Good day and welcome back. This is our second video on the topic of vectors. In the first video, we really took a look at the geometric properties associated with the vectors, specifically vector addition and scalar multiplication. In this video, we're going to dive into more of the analytic or component-wise perspective. So analytically, we represent vectors in terms of their components. I think the simplest way to see this is just to visualize what's going on, first in 2 dimensions, then in 3 dimensions. So if we pick our favorite point here in the xy plane, let's maybe arbitrarily just think of this as being a1 comma a2. So whenever we're dealing with a point, we're going to represent that by having just standard parentheses. Whereas the vector represented by those coordinates, we're going to think of it as a vector going from the origin to that point. We are going to represent this vector using angle brackets. So A1, A2. And this is a very important point for us to pay attention to. Remember, vectors are always going to have an arrow over them to indicate that they're a vector. Points are indicated with parentheses. Vectors, in this more analytic perspective, are indicated by these angle brackets. Similarly, if we want to think of something in 3 dimensions, the idea is identical. So if we have our x, y, z, once again, pick our favorite point. It doesn't matter which one, a1, a2, a3. And if we have a as being the vector connecting the origin to that point, we represent it analytically in angle brackets, a1, comma, a2, comma, a3. And a very important observation I would like to make is that in component form, and by component form I mean exactly what we're seeing here when we listed out a1, comma, a2, a1, a2, a3, those quantities are called the components. In the component form, a vector always represents what we call a position vector. And what a position vector would be, so that is, the origin is always the initial point. And let me go ahead and illustrate this with an example. So working in 2 dimensions, I'm going to go ahead and sketch 2 vectors. So I'm going to let v be the vector that goes from the origin to the point 1, comma 1. And I'm going to let u be the vector that goes from the point 0, 1 to 1, 2. And I would like you to take just a moment or two here, pause the video, and just compare and contrast these 2 vectors. And the observation that I make is as follows. So u and v as vectors, note they both have the same direction and magnitude. They both go 1 over in the x direction, 1 up in the y direction. So by our previous definition, u and v are equivalent. And remember, we don't talk about vectors as being identical or equal. We only talk about them being equivalent. So even though u and v are equivalent, note that v is a position vector, i.e. its initial point is at the origin, whereas u is not. Now it turns out that when we have vectors represented analytically in terms of their components, it becomes very simple to quickly add, subtract, or multiply by scalars. And the really nice thing is that we do exactly what we might expect. So if we want to add together 2 vectors in component form, as long as they have the same number of entries, you just add together all of those corresponding components. And there's nothing really special about addition over subtraction. And it works out exactly the same way. If you want to subtract two vectors, you simply subtract those corresponding coefficients. And if you want to multiply by a scalar, we simply take that scalar and we push it into each of the components. So this would be CA1, comma CA2, comma CA3. And something else to introduce just in terms of notation, for convenience, we will introduce V sub n to be the set of all n-dimensional vectors. And for example, we will work most frequently with three-dimensional vectors. So V sub 3 is the set of all three-dimensional vectors. So that would be all vectors of this form A, comma B, comma C, with the restriction that A, B, and C are real numbers. And let's go ahead and finish up our discussion on the analytic perspective of vectors by looking at a very common example. More often than not, this will be just a very small part of a larger problem as we move into future sections. So what we'd like to do is find a position vector connecting some point A to another point B. And the book gives a formula that one can use to go about this, but I think the key thing to do is to be able to think about this as intuitively as well as quickly and as efficiently as possible. So I want AB to be a vector. It's going to have three components that will bring us from the vector A, the point A, to the point B. So individually, what I want to do is just think about how I would have to go from, say, this first component in A to the first component in B. I would have to go 1 unit, so +1, in that positive x direction. How do I get from the second component of A to the second component of B? You have to go 2 in that positive y direction. And similarly, to get from 2 to -1 in that third coordinate, you would have to go -3 in the z direction. So the idea, or kind of the hint to thinking about this, is really just to ask ourselves the question, how does each coordinate change? So AB as a vector, if I'm at A and I want to go to B, I have to travel 1 in the x direction, 2 in the y, and -3 in the z. And I also want to throw in there that if you think about it from the book's perspective, you can really just do some subtraction. You subtract away those coordinates. So we take the B coordinate and we subtract it away from the corresponding A coordinate. So 2 minus 1 in terms of x, 3 minus 1 in terms of y, and -1 minus 2 in terms of z. And that gets us there, just as easily. But I think in terms of remembering and being more intuitive with how things work, this perspective is definitely going to be my go-to method. So in the next video, we'll move on to some of the more basic properties of vectors. So stay tuned and take care.